to stream. Okay, welcome everybody. I hope that you're all having a wonderful day so far. I apologize that this has started a couple minutes late. Unfortunately, we've been having some Wi-Fi issues here, so I hope that everyone is able to hear and see us, or see the screen. And we will get started with the grade 9 class. As always, we are open to any questions that you might have about grade 9 math, so feel free to leave those in the chat and we can get things rolling. So I'm just going to check the sound here and we're all set to start, okay? Alrighty, you guys. So today's lesson is actually going to be about exponents. We had a request sent to us for exponent law review, and since the lesson that we did at the very beginning about exponents didn't actually get posted to our YouTube channel, I figured we could do a review either way. So to get us started, one of the first things I like to talk about when we learn about exponents, and again, welcome, this is the grade 9 class, just so I can put that there. The first thing I like to discuss when we talk about exponents is the concept of like terms. So for those of us who maybe haven't gone too far into this unit yet, the concept of like terms might be a little bit new for you. And so what we're going to discuss today is how we can know something is a like term. Alrighty, so first of all, when we're adding and subtracting exponents, not exponents, but like terms and polynomials, it's really important to understand how we can group certain things together. So what we're going to do here is I'm going to put out a whole bunch of numbers basically. So we'll have a 2x, we'll have the number 9, 7x cubed, 4x to the power of 8. And in each of these, the letter x just represents an unknown variable. And what that means is it's technically representing a number, but it's just a number we don't know yet. It's a mystery we have not solved at this point in time. But it's important to remember that technically that represents a number, and that way we can know what and how we can use these as like terms. But what's also important to remember is that like terms have to do with a couple of things. And I'm just going to keep writing a few more of these here just so that we can make sure that everybody understands what we're talking about. So that's 7. Oh my gosh. And again, if anybody has any questions that don't have to do with today's lesson, you're more than welcome to leave them in the chat. What we're really doing here today and every week is trying to answer as many of your questions as we have. This was actually a specific request, so that's why we're going over this stuff, but you're more than welcome to add your own materials in there so that we can all learn together. So what a like term is really is just a group or a pairing that you can put together and add and subtract. Okay, so one example that I like to use before we talk about the stuff that I'm writing here is if we have, groups of apples, and we also have groups of oranges, and we have groups of bananas. See if we can see that yellow. No, we cannot. So let's do this yellowish color. That's actually more of a banana color anyway. Okay, so when we're talking about groups of things, obviously you're going to talk about, for example, groups of apples, groups of oranges, groups of bananas, and when you're adding and subtracting in a more complex way, and somebody says, well, you have, let's put a different color here. Let's say somebody told you have 1 bushel of 5 apples and another bushel of 8 apples, and then you also have, 10 bananas, but then you also have, like, I don't know, let's say 7 bananas, and then here you have 20 oranges, and also, let's say 2, or we'll do 12 oranges. So in this scenario, when you're putting things into their groups, you're going to say, well, the apples go with the apples, and they can go in the apple group. The bananas go with the bananas, and they can go in the banana group. And then the oranges go with the oranges, and they'll go in the oranges group. So here in the apples group, you have 5 apples plus 8 apples. And here you'll have 20 oranges plus 12 oranges. And here you'll have 10 bananas and 7 bananas. So then here you can add this up and you're going to get 17 bananas. Oh, sorry guys, just 1 second. Sorry, I just needed to adjust something on the screen. Okay, so then we've got here, we're going to have 13 apples. Oh. And here we're going to have 32 oranges. So basically what's happening is that we're grouping things together. And that's really what the concept of like terms is. So if we go back to this area here, we only want to group things together that actually have the same format. And what that means is, for example, the format of 2x squared in this particular term, we've got a number in the front, which we call a coefficient. And you've got an unknown variable. And that variable is to the exponent of 1. Whenever we have an unknown number, like where it's represented by a letter such as x or b or y or whatever the letter is, and that letter does not have an exponent, then that letter is to the power of 1 technically. Okay? So in this particular case, we've got a coefficient and we've got an unknown variable with a power of 1. That's a width with an exponent of 1. Alrighty, so if I'm going to scan through the rest of these here, and I'm going to actually pick a color that I can circle these with, so let's go with orange. So I'm going to call this my orange scenario. I'm going to go through here. Well, the number 9 is only a number by itself. It doesn't have an unknown variable attached to it. So I know that this is not a like term because it doesn't fulfill the qualifications that I've already set out as in my first term. Okay, let's look at the second one. So here we do have a coefficient and we do have an unknown variable, but the exponent is to the power of 3. And therefore, it is not a like term because we're looking for something with a coefficient and an unknown variable with an exponent of 1. So I'm going to keep going. Here we've got 4x to the power of 8. Again, it has a coefficient, but it doesn't have the same power on the unknown variable. So we're going to leave that one alone. Now here is an interesting one. We've got just the letter x. But what I want you guys to understand is that when you have the letter x by itself, what that really means is 1x. And with no exponent being shown, I can assume, it's not really an assumption, it's a fact, that that power is to the power of 1. So here I actually have found a like term. Okay, so I'm going to create a like term box over here for this particular like term scenario. And I know that 2x is a like term. I know that x by itself is a like term here. And I'm going to keep going, but I'm not going to go through them one by one just now because we're going to try another example. But I'm going to go through and see, is there anything else in this list that fulfills those criteria? So again, we've got a coefficient, an unknown variable x with an exponent of 1. So I'm keep on going. This next one is a no. Next one is a no. I don't see anything. Now, as I get to the very end, I see that I have this one here, which is 14b. And something that I've noticed with a lot of kids is that they'll assume that because this also has a coefficient and this also has an unknown variable to it with an exponent of 1, that this is going to be a like term. But what I want to really, really impress upon you guys is that this is not a like term with anything that has an x because it uses a different letter. And what the assumption is that if this was in an equation, then we would know that the letter b represents a different number than the letter x, and therefore they cannot be like terms. Okay? Now, if anybody has questions about that, let me know. We're going to try another one now. So another thing that I find confuses a lot of people is that when you have numbers by themselves, well, when you have a number by itself, whether it is negative or positive, it doesn't matter. It is considered a like term with other numbers. So here I've got the number 9, and I'm going to keep on going through my list to see if there's anything else that fulfills the criteria of just being a number. Well, right here we've got the number 3, so that's great. We can add that to the like term for numbers by themselves. We can have the number 7 in the like term box for that. And I don't see anything else that's just a number. So here's my like term box here. And I'm going to put in the numbers 9, 3, and 7. Wonderful. So here we've got just numbers. And then here we've got coefficient with unknown variable x to the power of 1. Okay, guys. Great. So that's that. I'm trying to write neatly, you guys. Sometimes it takes me a little bit of time at the beginning of every freemathhelp.ca to get my writing skills back to where they are, because obviously I don't do this during the week. So, okay, let's look at the next one. We've got 7x to the power of 3. So I'm going to use my pink marker here and see, what about 266? Oh, you're right, Flochi, 266. I totally missed that. Thank you for calling me out on that. Okay, let's go back. She's correct, or they are correct, I'm assuming. And we've got 266 is also part of the number squad. Wonderful. So we'll add that there. Thank you for checking on that. And that's the importance of really just being aware of what you're writing, because clearly I'm trying to talk and walk at the same time, I guess you could say. And we're all set. Yeah, so thank you, Flochi. I appreciate you calling me out on that. Okay, so now we're going to check out 7x to the power of 3. So what are the stipulations, or what is it that we're looking for here? Well, we're looking for a coefficient with unknown variable x, but the x is to the power of 3. So I have to make sure that I'm keeping that in mind. All right, so let's look at what else we've got here. I've got other unknown variable x's, but these ones on the top row are not to the power of 3. But right here, I've got negative 5x to the power of 3. So both of these qualify in this category. So these are both like terms, which means they can be added and subtracted together. Okay? Now let's keep going here. Nothing else to the power of 3 that I can see. So we're just going to leave that the way it is. Wonderful. So let's go ahead and use purple now for, let's see here. I'm going to skip this next one. I'm going to go over to 3x squared here. So in my 3x squared situation, I need a coefficient with unknown variable x squared. And I know this might seem a little bit redundant, you guys, but it's really important that we understand this fundamental concept because so much of math is predicated on this idea of like terms and being able to recognize what is and is not a like term. Okay, so 3x squared, that can go on my list here. What else do we have? 45x squared also falls into that category because it's got a coefficient, it's got x squared. Wonderful. Then 9x squared also. And 19x squared down at the bottom here. Okay, so that's the purple squad. Everything in place. And if I'm missing anything, guys, feel free to call me out as Flochi did already. All right, so up next, we've got a couple things left. We've only got 4x to the power of 8, 9b squared, 14b, and 17x to the power of 4. So none of these are like terms, so I'm just going to give them each their own number, their own section, I mean. So 4x to the power of 8. You know what? That red is too similar to the pink that's right next to it, so I'm going to pick something else. Let's just use black. So 4x to the power of 8, that can be 4x to the power of 8 in its own box. And again, coefficient with unknown, just going to use shorter terms here, variable x to the power of 8. Okay, you guys. So really the whole point of this is that these terms can be added and subtracted from each other in the sense that they're basically like saying, for example, we're just going to move this all up quickly for a second. So for example, if I was to add and subtract the numbers that I've got so far, and again, like I said, these ones that are left are just their own terms, so I'm not going to worry about them right now. We'll deal with them later. But basically what we're saying here is that if I was to bring these together, and usually what we like to do is we like to bring the ones with the largest exponents to the front. So let's go ahead and do that. So we've got 4x to the power of 8 here. And then we'll add up what else we have left here, which is 17x to the power of 4. And we also have some b terms here. So I'm going to leave those b terms just for the moment. We'll deal with those last. But then we're going to go ahead and have the 7x to the power of 3 minus 5x to the power of 3 from right over here. And then I'm also going to bring in these crazy numbers. We've got 3x squared plus 45x squared. And I'm using positive signs because whenever we don't see a sign in the front of a number, we assume that it's positive. So then we've got 9x squared and 19x squared. And then from there, we're going to go ahead and take these 2x to the power of 1. Because again, I'm going downwards in terms of the exponent. X to the power of 1. Then I'm going to bring my b terms in, involve them, because I have two b terms here. One is 9b squared. So plus 9b squared plus 14b. So again, I've checked these off my list. They're all separate. And then last but not least, I've got my numbers, which I'm going to add my numbers way over here. So let me just memorize them. 937226 plus 9 plus 3 plus 7 plus 226. So if someone asks us what all of this equals, we can actually tell them because what we're going to start doing is grouping things. So 4x to the power of 8 does not have any like terms, so that's going to stay the same. 17x to the power of 4 is the same situation. It does not have any like terms. But now up here we've got 7x cubed minus 5x cubed. Because again, it's like saying 7 bananas minus 5 bananas. So we can actually take those numbers and put them together. Okay, so I'm just trying to see what color I use. So we use pink, pinkish, I guess we could say magenta-ish. So these two terms are together, and here they're going to turn into minus, or not minus, so 2, so positive 2, my bad, sorry guys, 2x cubed. Great, so that's the 7x cubed minus 5x cubed. Remember that their coefficients can be added and subtracted to each other, from each other. Next, we've got the x cubed coefficient variable situation. So all of these here, 3x cubed and 45x cubed, 9x cubed, 19x cubed, they can all be added together. So we're going to go 3 plus 45 plus 9 plus 19. And that gets us 76x squared. So that's this here. Okay. Alrighty guys, so moving on, we've got our x to the power of 1 situation. So here we're going to get our orange, bring these two together. So we've got 2x to the power of 1, x to the power of 1, which together equals 3x to the power of 1. And then up next we've got 19b squared. And if anyone's confused about anything specific, just feel free to let me know. Sorry, not 19b, 9b. So 9b squared does not have any like terms, so it's just going to stay the way it is. Same thing with 14b. Also does not have any like terms, so it's going to stay the way it is. And then we've just got our numbers, so we add our numbers together. 9 plus 3 plus 7 plus 226 equals 245. And our number color was green, so I'm just going to get that together, get our green. So remember, numbers can be added with numbers, obviously, as we've learned all throughout school. And then that's going to equal 245. Wonderful. So this is actually our final answer, and I'm going to just put it all in one color so everybody can see what I'm talking about. But our final answer really is all of these separate terms, because we don't know what the letter represents right now. So my final answer is literally just going to be 4x to the power of 8 plus 17x to the power of 4 plus 2x to the power of 3 plus 76x squared plus 3x plus 9b squared plus 14b plus 245. Okay, that's our final answer here. Okay? And if anyone is confused, just feel free to let me know. I'm happy to answer any questions about what we just learned. But again, we are going to talk about exponent laws today, which is a little bit different than this. This is more for the polynomials part of this unit, because we've got powers and polynomials. Powers meaning exponents, polynomials being this kind of stuff that we were looking at here. But what I want everyone to understand is that what's happening here is that we're not adding exponents, we're adding coefficients. We're adding the numbers that are attached to the unknown variable. Because again, it's like saying, it's like saying you have 4 bananas and someone gave you an extra 3 bananas and now you have 7 bananas. What we're going to learn in the next piece of today's lesson is not about this stuff. But understanding this is very important, because sometimes you will have situations in our exponent laws part where you actually have to really understand how the polynomials piece works. Okay, very good, you guys. So, looks like we've got a fun lesson coming up here. So it's very important to get these numbers organized to not complicate things then. Yes, Flochi, that's correct. So you have to make sure that the numbers are added together when necessary, because that's the most simplified version of the answer. And that's really what we're trying to get at all times, is the most simplified version of the answer. That's really the whole key to math, is that. So yeah, so thank you for that question. That's a really good point. It's really something that is important to understand. So thanks for teaching me how to organize this with boxes, because I wasn't taught that. Oh, I'm glad. Yeah, again, we can move back here just for a quick second. Not to this part. So I like to teach this way, and I like the format of doing this online, because it allows us to use all the different numbers, all the different colors to demonstrate this. And I find that this is something a lot of people really struggle with, which is why I try to make sure that all my grade 9s, and for our grade 9s that are in our math mastery programs, in our at Scholarly Elite Tutoring, we really, really emphasize understanding this. This is one of the fundamental concepts of math and of the type of math that you're going to be learning all throughout the rest of high school. So I really implore you guys to practice this. Look up, you can even just Google like terms worksheets. Very, very good practice, because you need to be able to understand this fully in order to continue to succeed throughout the rest of high school math. Okay, guys, so up next we're going to learn about exponent laws. And there are quite a few exponent laws. What I highly recommend is that if you are following along, I recommend writing these down because it will help you out in the long run. So first we're going to learn about a law called the product rule / law. And what this is when two of the same base are being multiplied, you must add their exponents. Now, before I get into the specifics of the product rule and what that means, I want you guys to I want us to first discuss exponents in general. Okay. So what is an exponent? How does an exponent happen? I know that those of us who have finished grade 8 math have a little bit of an understanding of this from our volume and area unit, but I want to make sure that everybody is everybody's up to date. So if you have any questions, feel free to let me know. Now, what is an exponent? How does an exponent get created? Well, whenever we have anything times itself, so it could be the number 4, and this is a multiplication here. So 4 times 4 is 4 to the power of 2. Well, how did this happen? And why is it to the power of 2? Well, I'm going to give you guys a verbal example. Not a verbal example, but I'm going to give you another example that has nothing to do with numbers. So let's, for example, say, I was to say monkeys times monkeys. Well, that actually means that I've got monkeys squared. And the only way that this actually applies is when the base, or this term, like monkeys, or here we've got the number 4, right? That term has to be exactly the same. If it is not exactly the same, you cannot multiply the exponents. Now, why does it turn into the power of 2? We're going to talk about that in the next step. But what I just fully want you to understand is that when we have something times itself, that's when you get those exponents happening. It has to be the same base. So it could be literally x times x. That's going to equal x squared. It could be 5b times b. This technically has the same base because of b and b are the same. So you actually get 5b squared. So we're going to go into how and why this all happens. I just wanted to explain to you guys that when we have something times itself, it's really important to remember that it has to be the same base, okay? Now, let's bring this back up here. So as we discuss the exponent laws, again, what I really always like to make sure that our students understand is that you're multiplying things by themselves. They have to have the same base, and let's kind of see how that all works. So with the product rule, which again, if you guys are following along, I highly recommend you write stuff down. When you have two of the same base and they're being multiplied by each other, you actually are going to add their exponents. And I'm going to show you how and what I mean. So if I had the base of x, so this is the base, and to the power of 3, which is exponents, that's its exponent, or its power. Some teachers call it a power. Okay, so here I have a base and here I have an exponent. Now let's use this example. So we've got x to the power of 3 times x to the power of 7. Actually, you know what? That's going to be too many. Before we go into that, I want to show you what x to the power of 3 means. X to the power of 3 literally means x is being multiplied by itself 3 times. So it's going to look like this if I was to break it down. X times x times x. If I had this scenario where it's x to the power of 1 times x to the power of 1 times x to the power of 1, then I actually have 3 x to the power of 1s. And they're being multiplied by each other 3 times. Therefore, it becomes x to the power of 3. Let's do another example. If I had b to the power of 1, which is what that means, and then I've got b to the power of 2, another way of writing this would be b to the power of 1 times b to the power of 1 times b to the power of 1. And then the most simplified version of this would be b to the power of 3. Okay, so let's start applying this rule in a way that makes it a lot easier for us to actually go forward with our math. So in this scenario, if I had 4 to the power of 2 times 4 to the power of 21, instead of doing all of this that I showed you up here where I break it all down and I show you how it all gets to be where it is, all I have to write, because I already see that I have the same base, the base is the number 4. So what I have to do here is I'm going to go 4 to the power of 2 plus 21. And all that I need to write in my answer piece is 4 to the power of 23. And that's my answer. So this is the product rule, and I really need you guys to memorize this and practice this as much as you can. When two of the same base are being multiplied, you must add their exponents. Okay, so we're going to do another example here. I'm going to use another color. Actually, you know what? We're going to keep the same color, so we'll try to keep each area the same color. Just going to use a little squiggly line to demonstrate that that's separate. This is separate. This is separate. Alrighty, let's do a to the power of 5 plus, or sorry, not plus, multiply. Because remember, the bases are being multiplied in order for their exponents to be added. So times a to the power of 3. So again, I'm going to break this down for you guys so that you can see how this all happens. Okay, so a to the power of 5 can be broken down like this. A times a times a times a times a. That's 5 times. Okay, and these are all a to the power of 1. And then that's also times a to the power of 3, which is a times itself 3 times. And again, if I was to count these, 1, 2, 3, 4, 5, 6, 7, 8, then technically altogether, I have a to the power of 8. But again, I don't need to show this middle step because all I have to show is a to the power of 5 plus 3. It becomes one base, and then it becomes our final answer, a to the power of 8. Okay, everybody? So if you're confused by this, or if there's a specific part of this that you're not understanding, that's fine. It is a complicated subject, so please feel free to leave your questions in the chat. I'm happy to answer them. But if you're okay with that, we're just going to move on to the next rule. And we're going to be applying these rules in many different ways. So right now we're learning the basic rules, and then we're going to learn how to apply them together. We might have to finish that next week just because probably in half an hour might not be enough time to do all of it, but we will keep on trucking. We'll keep practicing. Okay, guys, so our second exponent law that's super important for us to understand is the quotient rule. So what is a quotient? A quotient is the answer to a division problem, and that makes sense for this rule's name because what this is actually when two of the same base are being divided, you must subtract their exponents. So let's go ahead and take a look at how this works. I'm just going to move that up a little bit and pick another color. Alrighty, so let's take a look here, what this means and how we can apply this. So let's say I have a base x. It's an unknown variable x. That's going to be my base. And again, it has an exponent. Let's call that exponent 5. Now, if I'm trying to use any of my rules, I know that the bases have to be the same. So over here, I'm going to start off with x to the power of 5. And then I'm going to use the same base, which is x, and divide that. So x to the power of 4. So let's reread the rule. Quotient rule. When two of the same base are being divided, you must subtract their exponents. So just like earlier, we're going to show you what that means. It's going to be x to the power of 5 minus 4, and that's going to equal x to the power of 1. Another way of saying that is just x. Okay, so this is our final answer. And if you recall from elementary school, a division doesn't necessarily have to always be written like this with a division sign. Sometimes it's in the form of a fraction. So we might have something like the power, the base b, unknown variable b, divided by b to the power of 4. And again, as with all of these exponent law questions, we're trying to simplify this as much as possible. So we're going to convert this into one standard base, and then just use this exponent to show the step of 9 minus 4. Alrighty, so and if you're following along, make sure you're writing everything down because it will make more sense that way. I'm trying to write a little bit slower this week so that you guys can write this down because these rules are quite important. So then we've got b to the power of 5. And b to the power of 5 is our final answer for that question. Okay. Oops, sorry, I didn't mean to hit the microphone like that. Alrighty guys, let's try something else. Something very similar, but it has its own kind of flavor to it. Closing that off. So let's say we've got 7 to the power of 9 divided by 7 to the power of 7. So our base here is the number 7. That's really important to note. And our exponents are 9 and 7. And here we've got a division. So just like in our rule, when we have a division of the same base, you must subtract their exponents. So this is going to become 7 to the power of 2, but we're going to show it like this, 7 to the power of 9 minus 7. And then in the next step, oh gosh, I wrote 9. Then in the next step, you're going to write 7 to the power of 2. And the nice thing about using numbers and not unknown variables in this scenario is that you actually are able to give a final answer that is just a simplified number. So if you have your calculator in front of you, let's try a couple different things. I want you to put 7 to the power of 2 into your calculator, and you'll see that you get 49. And then another way to accomplish that same goal is to times 7 by itself, because that's what 7 to the power of 2 means. It's 7 times 7. And our final answer is 49. So when you have numbers like this one, you don't want to leave them in their exponent form. If you can simplify them into just a single number, that's actually the best answer that you can give your teacher. So we've got 49 as our final answer right there. Okay, very good. One more example here for this rule. So remember, we're using the quotient rule. When two of the same base are being divided, you must subtract their exponents. So let's say I had 8 to the power of 9 minus 8 to the power of 8. So I want to show you guys kind of how this is another way to write this out. So we could rewrite this like this: 8 times itself, literally 9 times. I don't know why I use such large numbers to illustrate this, but that's okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Good. Another way that we can write 8 to the power of 8 is literally writing 8 times itself, 8 times. And I'm going to show you guys why we subtract their exponents and what the reason is behind how this rule works. So if you remember, any number divided by itself is the number 1. Would my teacher mark it wrong if I forget to do the final step to 49? That's a really good question, Flochi. So what the real answer to that is that every teacher is different, and ultimately it really depends on your teacher, but for the most part, teachers would dock a mark if you didn't put it in that final form of just a simplified number. Okay, sorry, I didn't see your question in time. I apologize, but yeah, so the most correct answer when you have a number like that is to actually put a final number just by itself. Okay, guys? So over here, I'm just going to show you guys how this works. So remember that 8 divided by 8 is the number 1. So here I've got 8 divided by 8. Cancel those out. 8 divided by 8. Cancel that out. So I can do that 8 times. Because right up until this last one right here, I can cancel everything else out. And that's why I'm technically left with the final answer, because if I was to do this the proper way, because obviously we're not going to do this every time, this is just to illustrate the point. If I was to do this the proper way with 8 to the power of 9 minus 8, then all I'm left with is 8 to the power of 1. Because that's all that's left when I'm doing this division, because these guys cancel each other out, and that's all that's left. So this is my final answer. 8 to the power of 1. You can also write it just as 8. It means the same thing. They're both the right answer. Okay? So I hope that makes a little bit more sense for you guys as to why this rule is the way that it is. It just wasn't raised right. That's the way it is what it is. But what are you going to do? I'm just kidding. Okay. So those are the product rule and the quotient rule. Again, if you're following along, we're going to try to get through as many of the rules as we can today. If we don't get through all of them, that's okay. We're going to just keep on trucking next week and keep on practicing, because this is actually a part of math that you're going to have to do on a much more complex level, again, in grade 11. So it's very, very good that you keep up with this work. Okay, so next we're going to learn about the power rule. So technically, the way that we can phrase this is to raise a power to another power, write the base, and multiply their exponents. And when we see it in writing, it can kind of be difficult to visualize. So what we're going to do is actually show how this works. Let me just make this a little bit. Oh, not trying to do that. Wasn't trying to do that either, but okay. There we go. This is the power rule. Made it look fancy, I guess. Hopefully you guys can read that. Alrighty. So let me show you what the heck this means, because when it's in writing, it can be a little bit difficult to understand. So what this is trying to say is when you're raising a power to another power, what this means is if you have x to the power of 3, and then that is to the power of 2, what you're really going to do is actually multiply those exponents. So the next step in this question would be x to the power of 3 times 2, and it becomes x to the power of 6. So let me break this down for you guys and show you why this means what it means. So what this is saying is x to the power of 3 times itself. Alrighty, well, another way of writing this is x to the power of 3 times x to the power of 3. Okay, and then if we think about our product rule that we learned a little bit earlier today, then all that's happening here is that you take their exponents and you add them together, and then you get the same answer. This is the same answer as this answer. Those are just two different ways of expressing this same concept. Obviously, this way is the more correct way, because that's going to help you simplify things on a much faster level. Like, it's just way easier that way. And this is actually the more mathematically correct way to show this. But I like to show both methods because it helps people understand a little bit. Another way of showing this, okay, I'm going to show you guys what this is also saying. It's like saying x times x times x, because that's another way of saying x to the power of 3, times x times x times x. And if you think about it, here we've got 1, 2, 3, 4, 5, 6. And that's x to the power of 6. So this is kind of a breakdown of why this happens. Again, I really only need you guys to understand how to do that first example that I showed you here. So I'm just going to leave the one that matters. And again, if you guys ever want to rewatch these, or if you have questions, feel free to leave them in the comments. But if you ever need to rewatch these, they're always uploaded to our YouTube channel afterwards. Sometimes it takes a couple hours for YouTube to upload it, but by tomorrow, this video will be on the channel and you can watch today's live stream back, or you can watch back live streams from other days in case you missed anything. Alrighty, so let's keep going here. Let's try another example. So I'm just going to put a little thingamabob there. So let's try the example b to the power of 4, and then that is to the power of 5. So again, using our power rule, we're going to say b to the power of 4 times 5. And then that's going to give us our final answer of b to the power of 20. Okay, very good. Up next, we're going to try something a little bit more difficult that is actually super important for you guys to understand. So I'm actually going to use a totally different color because I'm fancy like that. And here we go. So this rule also applies when you've got a fraction scenario. So let me erase some stuff because this is getting a little bit messy. So this rule also applies when you've got a fraction. So that would look like this. A to the power of 4 divided by b to the power of 5. And all of this is to the power of 2. So this is where these start to get complicated. And that's why I really want to teach this stuff in a way that breaks it down as much as possible. So what I first want to make sure that we understand is that BEDMAS always applies. BEDMAS, that fun little rule that we learned early in elementary school, it still applies in every situation. So what I first need to do in this scenario is ask myself, is there anything I can do in the brackets? So as I look inside the brackets, I see that I have two different bases. I have A and I also have B. Because they are different bases, there's nothing I can do. They cannot be divided by one another. Okay? At this point anyway, because we don't know what their numbers are. So a to the power of 4 divided by b to the power of 5 is going to be left the way it is due to the fact that those bases are not the same. If they were the same, then following BEDMAS, I would have to solve the inside of the brackets division first, and then I would follow my next step of exponents. But because nothing can be done, I'm going to leave it the way it is. And what I'm going to do now is follow my next step. So I'm going to show you guys how the power rule works when you have a fraction like this. This scenario basically means that we have to multiply in the number 2, both into the numerator and into the denominator. So the best way to show that is to write it like this: a to the power of 4 times 2 over b to the power of 5 times 2. And our final answer is going to be a to the power of 8 and b to the power of 10. And that's our most simplified version of this answer, and we leave it the way it is. Okay. Now I'm going to show you guys why this happens. So let's use another method of solving to show what's going on here. So I'm just going to show you this exact same problem and why it happened the way it happened. So if I've got a to the power of 4 divided by b to the power of 5, and all of this is to the power of 2, another way of showing this is to literally write it like this: a to the power of 4 times itself in the numerator, and b to the power of 5 times itself in the denominator. And then just like we learned earlier with our with our product rule, my bad, is that if we have the same base and they're being multiplied, we add together their exponents. So then we know that a to the power of 4 times a to the power of 4 is technically a to the power of 4 plus 4. And then here we've got b to the power of 5 plus 5. And then all we're going to get is a to the power of 8 and b to the power of 10. And that's our final answer, just like it was the last time, because these are the same. Okay? So again, these are just two different ways to show what's happening here. and why it is the way it is. So I hope that makes sense for you guys. And if anyone is confused, like I always say, feel free to ask away in the chat. That's what the chat's there for. Okay. Great. So we're going to learn something else now that has to do with this. And it's called the expanded power rule. So let me just write it out. So in the expanded power rule, you have to make sure to multiply in the exponent for all of the bases in the brackets. And I'm going to show you what that means. Let me just do this, move this over, get this. Whoa, try to make it so it's legible. Wonderful. Wonderful, you guys. Great. Okay, so let's show you guys what I'm talking about here. So in the expanded power rule, because like I said, these get pretty crazy, and it's really important that we understand the core fundamental values that are being, the word I'm trying to think of, I'm trying to think of a less fancy word than espoused, but espoused is really what I'm trying to say. Like, you guys need to understand the fundamentals here, because they will get super crazy, and those of you who have finished this unit probably know that these types of questions can be very, very intense. So let's go ahead and practice with this expanded power rule, and say I have something like 2a squared b cubed to the power of 2. So what I first want to make sure that we understand is that technically the number 2 is a base. Hopefully I spelled technically right. Oops. Technically the number 2, technically this number, we'll just say, number is a base to the exponent of 1. Because any number that you see by itself chillin' is actually a base to the exponent of something. Okay, so let's go ahead and apply this knowledge as best as we can. Well, first things first, what I really recommend to all my students, and what we teach our students at Scholarly Elite Tutoring, is that when you get a question like this, don't leave it up to chance. First thing you want to do is actually show that you understand that that base, that number, is a base. So I'll make that, instead of it just being the number 2 by itself, I'm going to write 2 to the power of 1, and then I write everything else exactly the way it was. All of that to the power of 2. So just like in our last rule, we need to remember that when we multiply in the exponent that's on the outside, we multiply it into each base separately. So it's going to be multiplied like this. And let's show how we would actually demonstrate that. So this would become 2 to the power of 1 times 2, because it's 2 times 1 there. And then a to the power of 2 times 2. And then b to the power of 3 times 2. And in our next step, we just do all of these multiplications. So here we get 2 to the power of 2, a to the power of 4, b to the power of 6. Now, remember how earlier, and actually Flochi asked that really good question about, will my teacher not give me full marks if I don't do the final step? So like I said, every teacher's different. I can't answer on behalf of all the Ontario teachers, but for the most part, teachers have been directed to dock at least half a mark usually for a situation where you might leave a number that has an exponent without actually expanding it. Because technically we know the answer to 2 to the power of 2. And if you're not sure, you can just put that in your calculator. It's the number 4. So this becomes 4 because 2 to the power of 2, or 2 times 2, is 4. And then the rest of these stay the same. And this is our final answer here. So this is our expanded power rule, and it's super important to understand that, because you really want to make sure, and because this is really where most people lose marks, is that they're not showing that work. They're not showing that 2 is a base. Okay, let's do one more example in this question area situation. Okay, so we have a similar question here. We've got 3x to the power of 9, y to the power of 7, and z to the power of 5. And all of this is to the power of 3. So let's say your teacher gave this to you on a test. This is very common type of question that you would see on a test. What do we want to do first? Well, like I said, how we teach all of our students at Scholarly Elite, put that in a rephrased version where you've actually put 3 to the power of 1, because that's what it technically is. And one tip I can give you guys for all of high school math, if you're in Ontario, is that in actuality, it's important to show every single step, because you're going to get those extra marks for showing all of the steps. Even though maybe one step is something that you could have done in your head, that's okay. Write it down on the piece of paper. You're going to get those extra marks for it. Okay, so next we're going to go ahead and do these multiplications. So I've got 3 to the power of 1, and then to make that to the power of 3. So what's that going to be? Up here we're going to write 3 to the power of 1 times 3. Then we've got x to the power of 9 to the exponent of 3. Well, that's going to be x to the power of 9 times 3. Then we've got y to the power of 7 times 3. Now let me just show that. And we've got z to the power of 5 times 3. What I really want to stress, you guys, is that you do these slowly. Do not rush through them. That's probably where most people make the mistakes in these questions, is that they try to rush through them because, you know, they seem simple on the surface, but it's actually something where you need to be aware of what you're doing. Okay, so then we've got 3 to the power of 3, because 1 times 3 is 3. Then we've got x to the power of 27, because 9 times 3 is 27. Then we've got x to the power of 21. Oh, sorry, y to the power of 21. And we've got z to the power of 15, because again, 5 times 3 is 15. And finally, again, we're saying to ourselves, well, this has a number to the power of itself, and I need to solve for that. So I'm going to go 3 to the power of 3, which is 27. Another way to say that is 3 times 3 times 3. So we've got 27, x to the power of 27, y to the power of 21, and z to the power of 15. And that, my friends, is our final answer. Okay, you guys, so that's everything for the grade 9 class today. We are going to continue the exponent laws lesson next week because we did not get to go through all of the exponent laws. But I thank you guys for joining us, and I hope to see you again next week so we can wrap up this unit, or at least the exponent part of this unit. And as always, if you have questions, feel free to email them to us at admin@scholarlyelite.com, or you can just go to our website and fill out the form and you can get right through to one of our advisors. But yeah, so talk to you guys next week. Have an awesome day and hope you stay safe out there, and we'll talk to you soon. And if you are just tuning in, welcome to the grade 10 class. I'm going to just switch over to another book here. Make sure I have all my grade 10 material. And give me one quick second. To make sure that I've got the right information. Okay, so we're just going to get started. Alrighty, so if you were tuning into our grade 10 live stream last week, you would have seen that we learned about SOHCAHTOA. Now, I'm going to quickly refresh us on what SOHCAHTOA is, and then we're going to learn about something called sign law. So, let's go ahead here. Give me just 1 second to make sure I've got the right stuff. Okay. So, first we're going to do a refresher of SOHCAHTOA, and then if we have time, we're going to learn about sign law and potentially even cosine law. We shall see how much time we have. So let me just, now because for those of you guys who just tuned in, you probably didn't watch the grade 9 class, you would not know that we had some technical difficulties at the beginning. So what I need us to just do here is to make sure that I have all the free mathhelp.ca stuff in place. So Just getting my triangle. There we go. Okay. So last week we were learning about right angle triangles and the rules that apply to the right angle triangles. And what those rules, or not rules, but identities as we call them, can be referred to as is SOHCAHTOA. So, oh, not my pencil. So if we've got SOHCAHTOA. Now, SOHCAHTOA only applies to right angle triangles. So I'm just going to make sure we have that down. So what is a right angle triangle? It's a triangle that has a 90-degree angle in it. And by way of the fact that it has a 90-degree angle, oops. So considering the fact that it has a 90-degree angle, we also know that there are a couple things that are standard. First is that this side length that is opposite the 90-degree angle is called the hypotenuse. Okay. Another thing that we want to make sure that we understand is that when we're talking about SOHCAHTOA, we're technically referring to a particular type of angle. So you're either talking about one of the two angles that are left in the triangle. So if I'm talking about this angle, and I'm going to use this symbol, it's called theta. Theta is a Greek symbol, so that's what it looks like. That's one way to call it. You can call it theta. What theta really means is unknown angle. So if I'm solving for an unknown angle, or just in general, I'm using SOHCAHTOA to solve a triangle, which means I'm either solving for a side length or the angle in question. What I need to be aware of is which theta I'm solving for, which angle. Wow, I wrote unknown with two N's, my bad. Which angle in particular do I care about? And what I'm trying to show here is that I care about the angle that's in the bottom right of this triangle. And what I'm going to do is now label the other two sides based on the triangle's angle that I'm actually referring to. So in this case, what's the angle, what's the side length that is right next to that angle? Well, that's this one here, and I'm going to call that the adjacent side length. And then what's the opposite? Well, what's right across from it? That's its opposite angle. So that's the opposite. Wrote that like a topsy-turvy clown. Goodness, there we go. Okay, so this is very important for us to understand, is which angle is which. Now, I don't want to repeat too much of last week's class because obviously we have other stuff to learn, and if anyone missed last week's class, I highly recommend you just go back onto our YouTube channel. You can watch all of the previous, or not all of them because the first couple weeks are not on the channel, but you can watch a bunch of the previous classes that we've done, just so that you can catch yourself up. But I am just quickly going to explain or reiterate what SOHCAHTOA really represents. So SOHCAHTOA, again, is a way that we are different kind of formulas, or they're not really formulas, they're more identities. They're called identities that we use to solve triangles for their angles and for their side lengths. How do we do that? Well, again, what I highly recommend for everybody is to have their calculators in front of them as we're doing this stuff, because I'm going to show you guys, or I'm going to talk to you guys through, I'm going to talk you through how to use your calculator to solve stuff. So if you look at your calculator, I have a very, very simple calculator. I actually recommend that you use the most simple calculator that is still a scientific calculator. So I use a calculator called the Casio. I'm going to write it down here because actually a lot of people ask me about this. The Casio FX991MS. This is the Scholarly Elite recommended calculator for high school. And actually, you can really use this calculator all throughout every math course. Like, I have used this for every university level math course I've ever taken, and it has sufficed and actually been more than enough. I've used it for calculus, stats, everything. It is a great calculator. So if you don't have a calculator, I highly recommend, if you can find one on Amazon, or if Staples has online delivery right now or whatever, this is really my recommended calculator for high school and university. Okay, so I'll get back to the point here. So the point is that on your calculator, and again, I have a Casio FX991MS, and on there I can see that I have the letters sine, cos, and tan. So really what these are just functions that we can use for certain angles. So if I was to press sine 45, I should get 0.707. If I was to press sine of 60, I should get 0.86. If I was to press sine of 30, I should get 0.5. So I'm going to show you guys what we do in real life to use the calculator in an effective way. So first I'm going to start with sine. So if I have sine of some angle theta, so again, that little weird sign is another way of saying angle. So sine of some angle is equal to the length of the opposite side, length, over the length of the hypotenuse. So in actuality, we are using side lengths of the triangle to solve for the angle, which is pretty cool. Cool in my definition of the word cool. I know other people have probably way cooler definitions. Okay, so let's look at SOHCAHTOA. We've got sine as our first thing. In the cos identity, we have cos of some angle, cosine of some angle, is equal to the adjacent side length over the hypotenuse side length. Great. And then last but not least, I've got tan of theta, which is equal to the opposite side length of the angle. Because remember, it's always relating to a specific angle. And then that is over the adjacent side length. Wonderful. So we can use these formulas both to solve for side lengths and to solve for the actual, what's the word I'm looking for? Angle itself. Okay? Now, what I want us to do is actually take a look at some word problems, because last week we went over these core fundamental solving, rules. And this week what I really want us to do is to understand how we can apply this to word problems. Okay, so I'm going to first type out this here. So just give me, so two buildings are 40 meters apart as illustrated in the given diagram. And I'll draw a diagram right after this. A point at the top of the shorter building. And sorry guys, I had intended to do this in advance, and then we had serious internet Wi-Fi issues right before we started the grade 9 class, and that did not go so well. So to the top of the shorter building, the angle of elevation to the top of the taller building is 37 degrees. From the same point, the angle of depression to the foot is 26 degrees. Okay, so for those of us who are new to doing this kind of stuff, this might seem very complicated, and that's why I picked this question, because I want to show you guys how it's actually quite easy to break these questions up. So first things first, if I'm in my math exam or my math test, I know you guys don't have exams this year, but if I'm in math and I've been given a question like this, the first thing I want to do is separate this into as many little pieces as possible. And this is actually a suggestion I have for all word problems, is try to see what parts of the problem can be segmented on their own. So first thing I'm just going to do is read it out loud. I'm going to say 2 buildings are 40 meters apart. That seems like a piece of information that's standing on its own. No pun intended. Basically, you just know that that's, one number you've been given, and that gives you 1 point of information. Next, from a point, or as illustrated in the given diagram, which we're going to draw ourselves. Next, from a point at the top of the shorter building, okay, I'm going to make that its own line. From the point at the top of the shorter building, the angle of elevation to the top of the, actually I probably wrote that wrong. Top of the taller building is what it should say here. Taller building, the angle of elevation to the top of the taller building is 37 degrees. So I must have typed that twice. There we go. So that's another piece of information. That stands on its own again. So I'm going to put that separately. And I understand that on a test, you obviously don't have the ability to mess around with the words like this. But what I do recommend is that you either have different colored pens or whatever, and you just circle pieces of information that are pertinent and on their own. So again, I've actually separated this question into 3 pieces because it has 3 separate pieces of information, and that's really what I need to know. And then from the same point, the angle of depression to the foot of the taller building is 26 degrees. Oh my gosh. Couple things I want to, oh wow, this is, oh, I see why it's not letting me do that. Gotta make this, gotta get. Hopefully it'll let me separate this. Oh my gosh, that's super annoying. I'm just gonna do this, you guys, so that you can see that it's separate. Okay, 2 buildings are 40 meters apart. That's one piece of information that I've been given. So I'm going to start over here and I'm going to draw a straight line. That'll be the distance between the 2 buildings. And then what I'm also going to do is actually draw the buildings, get a chance to use some of the fancy things in here. This. Cool. Okay. So this is, oh, I'm going to make this the shorter building area. So this is building 1. This is building 2. Cool. And then we know that they're 40 meters apart. So I'm going to illustrate that here. So I've got 40 meters. And honestly, you guys, the more you can draw these questions out, the better. Like if you're a person who likes to draw, give yourself a visual. It makes things so much easier to understand. So we've got building 1. He's got windows and stuff. It's a very avant-garde building with this crazy looking windows. This guy too. Very crazy looking. Looks like he's part of a Van Gogh painting or something. Doesn't really matter. I just want to illustrate that those are buildings. Okay, you guys. Another term that I want us to understand. First things first, we're going to talk about what is an angle of elevation. An angle of elevation is when you've got your baseline as being, let's say, like the bottom. And then what they're saying is, and I'm going to show you literally with a thingamabob here, if I could get that to work. Gosh. Okay, so let's say that this is my angle starting point. Pretend this is a protractor. An angle of elevation is where the angle goes up. So as I'm going up, the angle is increasing. Okay, that's an angle of elevation, starting from a flat point and going upwards. So let me just draw. Oh my gosh, there we go. Let me just pick this here. So this, where you're going upwards, this angle here, that's an angle of elevation. So let's talk about what an angle of depression is. An angle of depression, say you've got a flat line there. An angle of depression is where the angle starts at the top and goes downward like this. Okay, so this here is an angle of depression. This theta, angle of depression. So just remember the word elevate is up, depress is down. Okay, so let me put my line in here. So I've got my line, my imaginary line. So Actually, before we do that, let's walk through this. So it says from a point at the top of the shorter building, so we're going to start right at this point here, the angle of elevation, so that's at just my straight-ish, gosh. Okay, pretend that's like a dotted line, okay? So this is going to be our baseline. So because we're saying from a point at the top of the shorter building, that's going to be our baseline, and then we're saying the angle of elevation, I'm going to use a blue color here. Okay. Alrighty, so, oh, let me just use this angle here. So, what we've got to show is that the angle of elevation is going up. So I'm just going to show that because it's saying the angle of elevation to the top of the taller building is 37 degrees. So that's going to be 37 degrees. Great. And now what we're going to show is the next step, which is that the angle of depression, so from the same point, the angle of depression to the foot of the taller building is 26 degrees. So there we go. So there we are. So now I've been given all of this information, and what's really important to note as well is that these are actually right angle triangles. Okay, guys, I just need a sip of water. Give me 1 second, because I feel like I'm going to pass out. Okay. Alrighty, guys. So we've now drawn this situation. We've learned what angle of elevation is, angle of depression is, and remember, these are super important because basically what's going on is that you're going to see these terms in lots of word problems. So I'm just going to erase those there for now because the example illustrates what they are. And again, if you want to review stuff, it's always going to be on our YouTube channel afterwards. So by tomorrow, this whole lesson is going to be on the YouTube channel, and you can come back and watch it if you'd like. Now, basically the next part of this question is that they're going to ask, rounded to the nearest tenth of a meter, the height, which we're going to refer to as y, of the taller building is, or what is. Okay. So rounded to the nearest tenth of a meter, what is the height of the taller building? Okay, so we've got a couple situations that we need to solve for. This is a very multi-step question, and we need to start breaking it down as such. Now, one thing that we can assume is that obviously the bottom part is 40 meters, then that means from here to here is also 40 meters. And what I highly recommend for you guys to do is to actually redraw these triangles. So I'm going to redraw this first triangle. So I'm going to call this triangle A. I'm going to call this triangle B. And it just makes it easier for us to understand. And not understand, but for us to kind of visualize. So triangle A looks like this. We've got this situation, this side length is 40, this is 26 degrees, and this is 90 degrees. Not exactly my best straight line, you guys, but I think you get the idea. I'm just making it worse. We'll leave it the way it is. Okay. So I've got a couple of key pieces of information here, and another way that I can solve for what I need to know is using, or one of the ways I can solve for what I need to know is using SOHCAHTOA. Because in SOHCAHTOA, we're going to pick one of the three identities and go from there. So here's the information that's very important. Obviously, I know that this is the theta that I'm solving for. Okay, so in that way, I now know that I have one piece of information, and it's this side length, and I know that this is not the hypotenuse because it's not across from the 90-degree angle, So obviously I have to name it based on the angle that I'm talking about. So that's going to be 40 meters. And the 40 meters is our adjacent side length. So I'm just going to write that down because, again, as much information as I can get down is important. So adjacent is 40. Sorry guys, give me 1 second. I'm just going to check that everything is okay, because I think the sound is acting up. So okay, apparently it's fine now. Alrighty, so the adjacent side length is 40 meters. I know that the theta that I care about is 26 degrees. So now what I'm going to do, I'm going to go back to SOHCAHTOA over here. Where is it? SOHCAHTOA. And I'm going to ask myself which of these three identities has the adjacent in it. And that is the cosine and the tan. And what we're going to do is then going to go back here and take a look at what else we need to solve for. So we want to solve for this side length. Well, the reason for that is that obviously we want to figure out the height. And so this is one part of the height, right? So I want to solve for this side length, and that is the opposite side length. So that means when I'm looking at my identities, I'm going to want to know the identity that has the opposite and the adjacent, and that is tan. So I'm going to use that information. I've got tan of theta equals opposite over adjacent. And I've got a couple pieces of information that I can already plug in here. So tan of theta, so theta is 26 degrees, so I can plug that in. And I also know what the adjacent is, so I can plug that in as well. The only thing I don't know is the opposite side length. So the adjacent is 40 meters. Great. Well, given all of this information, what I'm going to do now is set this up in the way that actually your teachers are going to want you to set it up. So it's going to look like this. Tan of 26 degrees is equal to, we can call it anything we want. I'm going to call this x over 40. So we're going to solve for x. So just like we would in algebra, our next step here, which I'm actually going to have to move this up a little bit. Sorry guys, I'm going to cover the question a little bit just so that we can have some space. So this is going to now need to be solved algebraically. Well, algebraically, what I would do here, because what's happening to x is that it's being divided by 40, and the opposite operation is multiplication. So I'm going to multiply both sides by 40. So this is going to be 40 times tan of 26 degrees equals x. And then at this point, obviously, you are not expected to do this in your head. That's what your calculator's for. You're going to go tan 26 times 40, and that is 19.5 meters. X equals 19.5 meters. Okay, guys, so this is triangle A that we just solved. We just solved x here for this part. So we just solved this part of the height, but we're not done yet, because we still need to do the next part. So I'm going to do that over here. See how we get. I'm going to change the color just so that we can differentiate that a little bit. So we've got triangle B. And in triangle B, it looks like this. Oh my gosh, my straight lines, you guys. Whoops. So we'll do that, and do that. Okay, so again, this is a 90-degree angle, so that's going to be 90 degrees here. This is 37 degrees. And we need to know what this tall part of the building is. Well, just like I said before, if we know that the bottom part is 40 meters, then I also know that this here is 40 meters. This right here. Again, from here to here, that's 40 meters. So I know that. Now, what are we trying to solve for? We are trying to solve for this, and I'm going to call it y. And again, I'm going to try and sit back and think about what it is that I need. So in this case, I'm going to know that the 40 meters is my adjacent side length, and the reason for that is that it's the side length that is right next to the angle that we're using in this case. The y is the opposite side length, because obviously this right here is the hypotenuse. And we can just go ahead and use tan again, which is really, really helpful. So again, I always tell kids, one of the best ways to get higher marks in math is to really actually just write the equation that you're going to use, the formula that you're going to use, before you even start plugging numbers in. So tan is opposite over adjacent. I'm not going to write the whole words just because I see you guys have this over here now. And then I'm going to plug in the stuff that I know. So I know that here the theta is 37 degrees. I don't know what the opposite side length is, but I do know that the adjacent is 40 meters. Okay, that's a lot of really great information. So let's actually just start using that. So again, I'm going to use the opposite side length. Instead of using the word opposite, I'm going to write the letter y as our unknown variable. I'm going to write 40 there. I'm just going to follow up over here, you guys, just so that everybody can see. Okay, now, again, the same concept applies. It's going to be 40 times tan of 37 equals y, and that answer can be found on your calculator. So again, take out your calculator, press tan first, then write 37. You don't need to write multiply or add or whatever. It's literally just you press tan, and then you press 37, and then equals, and you should get 0.75, and then you multiply that by 40, and you'll get 30.14, but I'm just going to round it to 30.1 because they've asked us to round it to 1/10 of a meter. Wonderful. And this is in meters. Okay, guys, so my final answer now is just going to be x plus y, because here we go. We want to know the height of the tall building. And the only way to do that is to add together these two numbers. So that's going to be in purple over here. So I'm just going to do that. Height of building is x plus y equals the height. And the height is equal to 19.5 meters. And again, it's really important that as you get to the end of these kind of questions, you're using the units that they've told you about. That's really one of the keys to getting full marks on word problem questions. And then you just add these together. So then you get 19.5 plus 30.1, which should get you 49.6 meters. And that's our height. And because it's a word problem, you would write a word problem, like an answer. You would write a sentence. Alrighty, you guys. So questions like this can seem very convoluted when you are reading the question. Like I said, it's important to break down the question into as many little pieces as you humanly can, because it does make things a lot easier. Okay? We're going to do another word problem in just a minute. But if anyone has questions about how I solved this problem, feel free to drop them in the chat. I'm happy to answer them. Okay? Alrighty. So, we're going to move on to another question, you guys. Just give me one quick second to make a note of something that I have to do later before I forget. Because when you're an adult, you start to forget things. Alrighty. Great. So, just going to double check which question we want to do here. I will say one thing. This unit has an egregious, just an offensive amount of word problems. They love to mess with you guys using word problems in this unit. I really recommend you follow the strategy I taught you up here, which is that when you're given a word problem, you break it down into as many little pieces as you possibly can, because it will help you so much, you guys, I promise. Never try to rush through word problems. Really just analyze them from all angles, no pun intended, and, you know, give yourself that time to solve them. So that's something I always want to note. Alrighty, guys. So let us do okay, let's do this problem. I'm gonna write it out here. So I'm actually gonna put this in black just because I feel like it looks fancier. Okay, a ladder. Oh my gosh, why didn't it change color? That's not very nice. Whatever. Okay. A ladder sits between two trees at a point 3.5 meters from the base of the first tree. The ladder makes an angle of 70 degrees with the ground when its top is placed against the tree. If the ladder is turned and its top is placed against the second tree, with the foot of the ladder remaining in the same location, the ladder makes an angle of 66 degrees, as shown in the diagram. So we're going to draw the diagram based on this information, because a lot of times on tests you guys won't be given the diagrams, and so that's what I want us to really learn today, is how to use the information given to create diagrams for yourselves. Alrighty. So carrying on, first things first, we're going to take a look here and say, what are the three pieces of information that have been given to us? Sometimes they'll give you more information. Sometimes they try to mess with you and they'll give you way more information than you actually need. This question in particular is not doing that, so I want us to kind of go through each piece separately. So first things first, a ladder sits between two trees at a point 3.5 meters from the base of the first tree. That's a very weird statement, and I'm going to show you how we can use that, or what that really is asking us. So let's see here if we have trees. Oh my gosh, we do have trees. I was hoping more for like a Christmas tree look, but that is okay. We shall use what is at our disposal. Okay, so I've got tree number 1 here. Don't love the look of it, but that's okay. That's tree number 1. And then I'm gonna also put tree, oh, not what I was trying to do. Looks more like looks like cauliflower more than a tree, but anyways. Who am I to judge? Okay. I mean, who am I not to judge as well, but nobody asked me, so that's okay. Okay, I'm just gonna try to make sure that these are elevated kind of the same. I'm gonna use our straight line creator. And again, the reason I'm taking my time here is, like I was suggesting to you guys, taking your time is really the best thing you can do on word problems, because I need you guys to really, really take the time to solve these in a way that's helpful for you. Okay? Okay, so what is this telling us? It says a ladder sits between two trees at a point 3.5 meters from the base of the first tree. So what I first need to draw is that, basically that base, right? So here we go. First of all, I'm going to take it from here, and let's say that this is 3.5 meters. I'm just arbitrarily putting that there. So let's say from here to here is 3.5 meters. Great. Now, I'm also going to start erasing some of these trees so that I can put in my straight lines to show you guys what I'm talking about. What I'm going to do is use a different color for the straight lines. We're going to use green because we're talking about trees. Talking about trees, you know? So there's that. And here's the other one. Yee. Beauty. Okay. So the ladder makes a 70-degree angle with the ground when its top is placed against the tree. Alrighty. So what that's really saying, whenever you see the words makes an angle with the ground, usually what that's saying is, obviously, you need to start, and I'm going to show you kind of how I solve this. Like, not how I solve it, but what I'm actually trying to show when it says an angle with the ground. Well, that means I'm going to start at the ground and move my angle upwards to make that angle. And that right there, my friends, is going to be our 75-degree angle. So actually, I just need the pencil here. So, or sorry, not 75, 70 degree. So that right here that I just drew, that's a 70-degree angle. And I know, based on everything I've just done, that this is a 90-degree angle. Okay, so there's that. Then it says if, oh, I wrote the word and wrong, but it's okay. If the ladder is turned and its top is placed against the second tree, with the foot of the ladder remaining at the same location, the ladder makes an angle of 66 degrees, as shown in the diagram, which we're going to draw right now. So let's go ahead and use this information to our advantage. Get a different couleur. So on this side, again, so it's saying if the ladder is turned and its top is placed against the second tree, but again, these are just words they're using to confuse you. Do not let them confuse you. All they're saying here, the important part of this sentence is that the ladder makes an angle of 66 degrees with the second tree. So again, I'm going to start at the bottom because it's saying it makes an angle of 66 degrees and we're assuming that it's with the ground, obviously. And you draw this part here to be 66 degrees. Okay, and then I'm also just going to put this second thingamabob. Oh, started that a little too far. There we go. Okay, you guys. So here we are. Wonderful. Again, that's a 90-degree angle. So we've got a little bit of information that we can use to our advantage. We are assuming that the trees are the same height. Okay? And before we start anything, I'm just going to give you guys a second to copy everything down if you are following along, and then we can get started. Okay. So, what the first part of this question is going to ask is, what is the length of the ladder? Length Okay. What is the length of the ladder to the nearest tenth of a meter? Alrighty, you guys. So, let's go ahead and solve for that. Well, we know a couple of things. So we know that a ladder sits between the two trees at a point of 3.5 meters from the base of the first tree. It makes an angle of 70 degrees as it's turned. Sorry, an angle of 70 degrees with the ground when its top is placed against the tree. Which means now that this right here, our hypotenuse, is also the length of the ladder. Okay, if anyone is confused by that, just let me know. But I think for the purpose of what we're talking about, this should make sense. Alrighty, so now what we're going to do is solve for the side length of that hypotenuse. Well, again, because when I'm solving using SOHCAHTOA, which I'm going to write over here, SOHCAHTOA, and I implore you guys to memorize SOHCAHTOA and the letters in it. That's really going to help you a lot. I have to use the angle that I'm talking about. So in this case, I'm using the 70-degree angle that we've got here. That's our theta that we care about. And I'm then going to go ahead and solve for the other side lengths in the sense that I want to determine names for them. So the 3.5 meters right here, this is actually the adjacent side length. Okay, so what I need to do now is say, okay, well, what information do I have? I have the theta as 70 degrees. I've got the adjacent side length of 3.5 meters. And what do I need to solve? Well, that's the hypotenuse, which we don't know. So that information tells me that I need to pick the identity that is using the adjacent and the hypotenuse, and that is our cosine identity. So I'm going to write that out. I've got cosine of theta is equal to adjacent over hypotenuse. And I'm going to then take the information that I have and plug that in. So it's just going to be cos of 70 degrees is equal to 3.5 times the hypotenuse. And instead of writing hype, I'm actually just going to call this x, because that's an unknown variable that we're solving for. Okay, you guys, given all of this information, what's really important to understand is that if you have trouble solving these, typically what is causing that trouble, and I don't want to assume that everybody is the same, and not everybody is the same, but in my years of tutoring, I would say like 99% of kids struggle with these types of questions because they're not sure how to apply their algebra rules. Okay? So what I want us to understand here is that there's another kind of mindset you can use when you're solving these questions that will help you out. So what I would usually recommend to my students is, instead of using this as a way of figuring out where the x should go and how you can isolate for x, what I usually would do is I would say, okay, 10 equals 20 over x. Obviously, these are not the numbers that we're using for our problem that we're solving, but it's going to help us determine how to use this. So in algebra, the way that I would solve this is I would first multiply up the x. So that would become 10x equals 20. And then in the next step, let me actually make this wider. Hopefully you guys can see it a little bit better. Okay, so then in our next step, what I'm going to show here is that I need to isolate x. So I'm going to multiply or divide off the number 10 off of both sides, cancels on this side, and I get x equals 2. So how can I apply these same rules? This is part 1, part 2, part 3, part 4. How can I apply these same steps to the thing I'm doing over here? It's actually very easy. Okay? So just like we did here, I'm going to multiply the x upwards. Let me just get the right color here. So I'm going to get x times cos of 70, which I leave the way it is. Oh. X times cos of 70 equals 3.5. And then, so that's step number 2. So this is step 1. This is step 2. If we're following along based on what we did earlier, I'm going to move this up so that we have some more space to show. Up next, we've got step number 3, which is dividing off cos of 70. So it's going to be x times cos of 70 divided by cos of 70. And I would just leave cos of 70 the way it is right now. Don't actually solve it on your calculator yet. Just write the letters, letters and numbers, cos 70. Great. This cancels just like it did over here. And then in the fourth step, you're left with x equals 3.5 over cos of 70, which you can actually plug into your calculator. What I would recommend is that you put these in brackets. So you put 3.5 in its own bracket and then divide by bracket cos 70 to get that answer really clean. And our x here is equal to 10.23, which can also just be rounded to 10.2. 10.2 meters, is the height of our ladder. So that's really useful information. I can actually get rid of all of this and then just go ahead and plug that in here, 10.2 meters. Okay, so now the next part of this question, because we do still have a couple more minutes, so I'm going to solve the next part of this question as well. So that's this part. I'm going to actually just let you guys write this down. There for a second. Oh, can you actually see that? Let me bring this up a bit. I'm going to erase this in a second just so that we can keep using the image. So I'll let you guys write that down and then we can go from there. Alrighty, so we're going to erase that and we shall go ahead onto the next part. So we solved for the length of the ladder. We know that it's 10.2. And what we're going to do now is solve the next part of this question. So we solved the length of the ladder, and now the next part of this question is asking us to the nearest meter, to the nearest tenth of a meter, what is the distance between the bases of the two trees? Great. So we're going to take that, move it over here. So this is what we're solving for now. To the nearest tenth of a meter, what is the distance between the two trees? Oh, how did that do that? Just going to re-erase all this. Alrighty. So, oh my gosh. So this is actually not that crazy. I don't know why I'm using my mouse. I should just be using my tablet here. Way easier. Alrighty, you guys. So this is actually not too crazy because we've already solved a really critical part of this question. And that is the length of the ladder. Because if we go back to the original question, to the OG question, it says, in the third part, it says, if the ladder is turned and its top is placed against the second tree with the foot of the ladder remaining in the same location, meaning just right there in the middle, if the ladder makes a 66 degrees, the ladder makes 66 degrees with the height of that other tree. So let's go ahead and use that information to our advantage. Because we know that the length of the ladder is the same either way, this is 10.2 meters. Okay, because this is the ladder, obviously, up against the tree. What we're really solving for here now is this. We don't know what this is. So I'm going to call it y, because altogether we want to solve for what's going on here. Now, in this case, in the last case, we knew the adjacent and we didn't know the hypotenuse. In this case, we know the hypotenuse length, but we don't know the adjacent length because we care about this angle here, 66 degrees. That's the adjacent there. And what's going to happen is we're going to try to solve for the adjacent. So I'm going to write down the stuff I know. I know the hypotenuse length is equal to 10.2 meters. I know that the angle theta is equal to 66 degrees. And I don't know the adjacent, but that's what I want to solve for. So we can definitely do that. Again, we're going to be using cosine, because cosine of theta is equal to adjacent over hypotenuse, except in this scenario, we just won't know what the we won't know what the adjacent is. Alrighty, so let's plug in our numbers here. So we've got cosine of 66 is equal to some unknown variable y, because we don't know the adjacent side length, divided by 10.2. And then all we need to do is multiply up 10.2 times cos of 66. And again, on your calculator, you're going to want to put these in brackets. So put 10.2 in one bracket times cos 66. Like you literally, in the other bracket, you put a bracket sign, then you put cos 66, nothing else, close the bracket, equals y equals 4.14. And they wanted this to the nearest tenth of a meter, so this is just going to be 4.1. Okay, so now all we need to do is take that information, plug it in. So right here, so this is 4.1. So we know if this is x and this is y, we're going to add these together. So we get x plus y equals the distance between the two trees. That's 3.5 meters plus 4.1 meters. And that is equal to 7.6 meters. Alrighty, guys. So I hope that that makes a little bit of sense. What I'm really trying to get at here is not that I want you guys to copy down exactly how I did this. It's more important to me that you understand the fundamentals of how this came to be solved. So a couple tips I have for word problems. First of all, don't let all of the word problem together terrify you or freak you out. Just take your time, split up the word problem sentence by sentence, read them and see what information is important. Draw your diagram. I highly recommend always drawing a diagram. In fact, typically in this unit, drawing the diagram will get you the full mark. And then from there, rewrite all the stuff that you know for each piece. So here I rewrote hypotenuse equals 10.2. Even though I had it drawn over here, it's really good to have it rewritten. It really helps you get those high marks. It also encourages your teacher to kind of see you as a person who does your due diligence, who does all of the work, and that will get you higher marks in the long run, I promise. And then you've got your theta, which equals 66 degrees. And then I always put the unknown thing. So this is a strategy I use for word problems. It's called guessa. So I'll show you what I mean. So in a word problem, you have a bunch of different things you've been told. So here I write down what's given, which is what I've done here. I wrote down what was given. Then over here, I'm going to write down the unknown, which I did in this part. I wrote, I did not know the adjacent, and that's what I'm solving for. Then I'm going to write the equation that I'm going to use to solve, which I did right here. The cos of theta equals adjacent over hypotenuse. That's my equation. And then I'm also going to write the solution, or sorry, the solve. So the solve is this part here where I'm actually doing the solving. And then I write my solution, and my solution is this part here. And then we start with, so some teachers call this just guess, other teachers call this guessa. It depends. Basically, I include answer at the bottom because in a word problem, you would actually want to write out a sentence saying, you know, the distance between the bases of the two trees is 4.1 meters, or sorry, the distance between the bases of the two trees is 7.6 meters. So that's kind of why I would have the A at the end there. All right. So I'm going to leave this up for about 30 seconds. If anyone has any questions, let me know. We're going to wrap up after this one. So if you guys have any questions for these last 5 minutes, let me know. Or 4 minutes, I guess. But other than that, that covers pretty much SOHCAHTOA, like how you would solve it in different scenarios, how we apply that knowledge in terms of our word problems. That said, if you guys are doing this unit right now and you have a certain type of question that you're confused by, you're more than welcome to send in questions. You can always send in questions either in the chat during the live stream or to this email address, admin@scholarlyelite.com, and myself or one of our team members will add it to the roster of questions that we'll deal with next week. Alrighty? But next week, we're going to continue this unit. We're going to get on to the sine law and learn how to use that, and then potentially even the cosine law, depending on how much time we have. But other than that, I thank you guys for joining. I think you're doing a great job keeping up with your math work. And if you do have questions, like I said, you're always free to send them in. But other than that, I hope you stay safe, and I hope you have a wonderful week until next time. So talk to you guys soon. I'll leave the question up for another 30 seconds or so. I'll stick around for a couple minutes, just kind of chilling, and then we'll shut down the stream at 3 o'clock. So have a great day, you guys, and we'll talk to you again soon. Bye.